Hey everybody, in this recording we are picking up where we left off in the previous video, and in the previous video it has a red title, red to like orange. This is going to go a little orange to orangey yellow, and we'll go through the rainbow with that so you could know what order all the videos are in. So in this example number 3, we are actually going to find the limit of the rational function, which actually happens to be the reciprocal, right? The reciprocal of example number 2. In example number 2, it wound up being a linear equation with a hole in it, a hole which is also known as a removable discontinuity. And the way we kind of deal with that hole in the graph is we kind of spackle it figuratively by, spackle with a little spatula. You basically cross out a common factor on top and bottom. Now, if the common factor in your numerator and denominator is just a constant, like 5, 2, -1, in that case, your graph will not have a hole because that constant value is not a wild card. It's not a variable. It cannot change. The word constant literally means stays the same, and variable literally means that it will vary. So a variable is a wild card because we don't want to put a number in there that'll make our denominator 0, since we're not allowed to divide by 0. Now, we also went over 3 different scenarios with 0. You can either have 0 over a number, you could have a number over 0, or you could wind up with 0 over 0. Hopefully we all remember which one's which. If you write it down on your paper, I did make a little visual trick for it for you guys. So again, if you have a number over 0, no, that is undefined. If you have 0 over a number, okay, that is 0. And if you have 0 over 0, look at that cute little cartoony division sign, and that just means we're going to divide and reduce. Spackle. I'm not sure how to spell spackle. I feel like it's not what I think it is. I want it to be this, but it's a brand name, I think, so it might be wrong. But divide and reduce, basically spackle, you're going to fill that hole. Now, sometimes you might divide and reduce, but still have a hole in it. That's definitely possible. We can talk about that. But in that case, you divide and you cancel and you still have a 0 on bottom. That would mean you have this, okay? So we'll talk about that when we get there. So, which we'll see in a minute. All right, here in this example, if we try direct substitution first, DS, I'll abbreviate. Direct substitution, what do we get? Well, that means I'm finding the limit. That means I don't write LIM in front. That means I will just get, for my next step, I will have 2 minus 2 over 2 squared minus 4, which is 0 over 4 minus 4, being real extra on this, I know, which is 0 over 0. So there we go. Yet again, we have our little division sign. So we're going to try to factor and reduce as best as possible. Again, I said it and repeated it a bunch of times in example 2. You cannot reduce that x with that x squared. No. You cannot reduce that 2 with that 4. No. If people do that, could they coincidentally and accidentally on this example possibly get the right thing? Yes, but only on this example. It doesn't normally work like that. So could it possibly by mistake get you the right thing for the next term? Yes, but guys, listen, that you can't do that. It's not a thing. Now, I'm going to go ahead. My numerator, vocab's important. The numerator is already a linear, first power, polynomial. Our factors, when things are factored, are usually what we call linear factors, okay? They're usually linear factors, first degree. On the denominator, what we have is a quadratic. This happens to be a quadratic binomial, and that means I'm going to try factoring. Some quadratics are prime, which means you cannot factor them. All right. This, though, is the difference of two squares. And we factor that, like we said last time, by using conjugates. And conjugates, like you conjugate a verb, you keep the beginning the same and you change the ending. And it's really the square root of x squared and the square root of 4 that get used. Plus and minus is what's responsible for the outer and inner canceling out. Carrying on. I don't need parentheses around this, but there are an invisible set of parentheses. Important to mention that because if sometimes they like to squeeze that negative sign right here, and they love blending it right in line with that fraction bar, so always watch out. But if you have a negative sign, it really would get distributed to your numerator. So even if there were no parentheses, if you gave it to the top, that numerator would become a negative x and a plus 2. So you do want to remember that there are little invisible parentheses around your numerator. Carrying on. If I go to reduce, that is me spackling, and that's going to be me taking care of this issue. So spackled. I just filled the hole. But the hole was in a graph. What graph? The graph that the hole was in is whatever the graph of what remains looks like. So I'm just going to rewrite my next step. I'm still looking for the limit as x approaches 2. So my x value will be getting closer and closer and closer to 2, positive 2 for x. But how do we get there? We have to be on the road. Where's the road? The graph. Whatever the graph looks like, wherever it is, you're going to take the graph and you're going to get closer and closer to 2 and see what happens. If you approach the same number, get closer and closer to that same number from both sides, bam, there you go. That number as a y value, the output, is your limit answer. If they're both going up to infinity, we would say the answer is infinity, and that doesn't exist because you're not approaching a number, but you would put infinity, you would put negative infinity, you would put does not exist. So let's see. What's left in my numerator? Right now that completely reduces. All I have left is a 1, and on bottom, I have x plus 2. So this right here, I used the phrase rational function last time. It's still a rational function. If I had to graph the numerator, that's a linear function. If I only had to graph that denominator, x squared minus 4, that would be a quadratic function. But something like this ratio, that is classified under the big umbrella of rational functions. Does anybody know what the parent function of this is? By name or equation? I feel like equation should be fairly easy to get a parent function. The parent function for this is the most plain version of that. So all you have to do is really like look for a way to get rid of all of your constants, except in most cases like a 1 being multiplied or a 0 being added. But we don't have 0 being added anywhere. We do have a 1 kind of multiplied or divided, multiplication, division, they're the same. So the 1 can stay, but the plus 2 I'm going to get rid of. 1 over x. The parent function 1 over x, do any of you remember the name of that, which also starts with an R? Or do any of you remember what that graph looks like at all?
Is it the reciprocal function?
I think I heard it. I think it just cut out a second, but I think you said reciprocal function.
Yeah.
Good. Yes. So y equals x, which is the parent function for a line. This is the identity function. So think about the word identity. Your identity, you are who you are, right? So that's the identity function. Sometimes they abbreviate function like F apostrophe N or something like this, like function, I don't know. So that's the identity function, y equals x. And what is the reciprocal of x? 1 over x. So that's why it's the reciprocal of the identity. Now, graphing the reciprocal function, it's just a specific name. We reviewed that months and months ago. I know it's been a while, and we've done a lot since then. But does anybody remember what the graph of it looks like? Or if you made a table of values, could you tell me some ordered pairs that would be on that graph? I'm just going to go 2 units in each direction. Let's imagine table of values. Input is x. We're going to put in 1 for x. If I put in 1 for x, my output is 1 over 1, which is 1. So I'll definitely have a point there. Most of your parent functions will pass through the point 1, 1. Not all. Something like the sine wave, y equals sine x, will not. Or actually, most of the other ones do. I can't even think of one off the top of my head. Exponential will not. And log will not. So there are cases that don't. But a lot of them go through 1, 1 and either -1, 1 or -1, -1. It won't go through the one under it because then it wouldn't be a function, right? Let's go some vocab right now. If a function is, it can be classified as either odd or even. I don't know how many of you remember dealing with that vocab last year. I know I did go over it, but an example of a function that is even would be something like the absolute value function, something like y equals x squared, the quadratic parent function, something like cosine of x, that's even. What else? Those are the main ones I would think of. And something that's odd would be something like y equals x cubed or the cube root of x, y equals x, y equals sine x. Those would be classified as odd functions. So sidebar before we go on, like I said, I'm building the review right into the limit questions, okay? So this side is odd functions. I'm just going to give some examples and go over the definition right now, and even functions. Now, does anybody actually, I feel like it's sometimes glossed over, or even if you did spend some good time on it, you know, you may have like completely pushed this out of your memory because you think of odd and even as just plain odd and even numbers. But do any of you remember talking about odd and even functions in Algebra 2? If you want to just press the hand raise button if you remember talking about it. If not, it's okay. But anyone that did. So nobody remembers. Okay. All right. So first case, examples. I just rattled some off. Y equals x. Y equals x to the third. Y equals the cube root of x. Y equals, well, I'm going to give it away, 1 over x. And y equals, let's throw the trig ones, sine x, tan x, cosecant x, and cotangent x. Even examples, y equals x squared, y equals the absolute value of x, y equals 1 over x squared, y equals c, comma, where c is any constant. Y equals cosine x, and y equals secant x. Those are the ones I'm just thinking of off the top of my head. Now, I know you might not remember all of those graphs, but if you remember some of them, does anybody think they can explain what the odds all have in common and what the evens all have in common? I'm going to sketch a little baby sketch of each parent function next to it. So I'll draw my axes in black, and I'm just going to use a color pen when I go in and draw the graph. But if you wanted to give it some thought, this would also be good for anyone who, make these a little longer. Anybody who wants like a quick like mini reference. We're going to go in into a more detail with a lot of these functions as we review limits anyway, but just a quick baby review. Over there. Okay. think red will show up okay. I'm just not sticking the arrows at the end to kind of save myself a little time. Oh, so much for that. I put arrows there. Those are all little baby sketches of these functions. And then here, I'll actually even change my pen. Let's do blue.
Are all the even functions symmetrical across the y-axis?
Yes. There you go. So that's one thing we got. So that's the visual. I hope everyone kind of can see that. Sorry, this is like not super well done over there. But do you guys all see what Zareen said about that? So all the evens are symmetrical over the y-axis. And there is another way that we describe this type of symmetry. I'm not sure if any of you remember talking about this other type of symmetry, maybe in Algebra 1, maybe in Algebra 2. But does anybody remember how you would describe the symmetry on these examples? So I'm going to write down what Zareen said. These are symmetric over the y-axis. Sorry, I kind of wrote it a little funny, but there it is. So these are symmetric over the y-axis. Obviously, I could go in with a highlighter and kind of show that line of symmetry right down the middle, right there, right there. Okay, so if I look at that green line, fold it in half, my graphs of an even function is going to be balanced, even, the same on both sides, at least for the parent functions. If you shift it up and down, usually you're still in the clear. If you stretch it, compress it vertically, you're okay. Reflect it vertically, you're okay. But if you start shifting it this way, things get a little funky and it's not going to be symmetric over the y-axis. It will have an axis of symmetry still, yes, but not over the y-axis anymore. Now these actually have a special type of symmetry. Obviously, no function can be symmetrical over the x-axis because it won't be a function, right? The way we describe these is we say that these are symmetric over the origin. And when someone says that something is symmetric over the origin, that just means that if you were to rotate it 180 degrees about the origin, it would land back to give you the same picture. That's what that means. Okay, so I'm going to write that out over here on the side next. Odd function, so I'll write this like phrasing different, have symmetry over the origin. And what does that mean? I just explained. A 180 degree rotation will get you back the original graph. Okay, so if something has symmetry over the origin, we consider it an odd function. And if something has symmetry over the y-axis, we call that an even function. Now, everything in math will also have like a more formal definition using notation like we saw with limits. So I am going to give you the formal notation definition for odd functions and even functions. So if you need to kind of revisit this, look at this picture later a little bit longer, you could just, I'll share the video right after class. But I just want to give you that definition. So let me slide this right over here. So I'll kind of leave a little bit of that part. Now, the way we write this, first we need to remember what function notation looks like. What's notation for function in algebra or in most math classes? What notation do we use for function? What do I write mathematically in an equation to represent function? No one?
F of X.
Yeah, Nolan, thank you. F of X. So odd, I could write two different ways. Even, we really just write one way. So I think I'm going to write the even one first. So even, the F of negative X is equal to the F of X. So think about that. It should make sense. If you have a function and you plug in a negative number and you plug in that same number but positive, F of something is the Y value. So your Y values will be the same. Does everybody understand that, or is anyone confused on that? Because I feel like not everybody really understands that F of X is an output or a Y value that you get when you plug in an X value. We keep it broad and general a lot of the time because we leave it as an equation or a formula that we can use. However, in a definition like this one, it just means the Y value of a function when you plug in a number, okay, the Y value of a function when you plug in a number is the same as the Y value of that function when you plug in the opposite number. Opposite, I hope you remember, means negative and positive, right? So if you plugged in 2 and negative 2, you get the same Y value. Cool. But that doesn't mean if you did it one time on one number, that doesn't mean definitely an even function. You can have one time something has some symmetry, but you need to prove that it's always symmetrical, and that's why we leave it with X, because X can be any number and it's a better definition, okay? Whereas here, I'm going to write it two different ways. You can either write the F of negative X. If I plug in a negative number, the Y value that I will get will be the opposite of if I plug in a positive number. That's one way that we could write that. So think about that like over here. If I plug in F of negative 2, if I plug negative 2 in here, I'll get negative 2, I'll get negative 8. So that'll equal negative 8. Does that equal the opposite of the F of 2? F of 2 is 8, and its opposite is negative 8. Check. Okay, that's just an example, but that's how it works. The other way you can write this, and obviously this is reversible, whatever way you'll see it presented to you ever, but I could also just write F of X if I wanted one side plain F of X. You would just divide by the negative or multiply by negative. So F of X is equal to the opposite of the F of negative X. It's really the same exact thing. I just took that negative and put it on the other side. As long as you multiply both sides by negative, it's cool. So those are just some formal definitions. Like I said, I'm building the Algebra 2 review right into the limit problems so that you could see exactly where and when they would come up. So I'll give it 5 more seconds for you to write this, but just to say, this comes in so handy, super useful in the end of calculus when you do integrals or antiderivatives, because you end up using those to calculate area underneath functions. And if you know that there's some symmetry involved, you can sometimes cut your work in half and double it. Sometimes you'll find the area. I'm just going to grab this little highlighter and kind of color on here. Actually, I'll use yellow, but you might end up finding the area like under this line and above this line. So they might say between this function and the x-axis. Well, if these triangles are the same size, obviously these are easy because they're triangles, but if they're doing like the sine wave, right? If I do this area and this area, well, I could just find 1 and double it, cut my work in half. Same idea, if I find the area under the parabola on both sides, I just do half that work and double it. You'll see that in the future, okay? So that's really handy if you could recognize even and odd functions. Anyhow, rewind, going back to our example. So 1 over x, this is an odd function. It will have symmetry about the origin. We could rotate it 180 degrees and get back the same picture. All right, now I'm just gonna use blue to actually graph this. If I plug in 1, I get 1. If I fill in -1, I get -1. That's why I brought up and started talking about graphs. 1, 1, and -1, -1. I got it here. I have it here. I have it on this one. No, 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 not on the trig. On these, the evens, 1, 1, and -1, 1, same, same, depends on the constant, and no, and no. But a lot of these, like really fundamental parent functions from algebra, pass through those points. Next thing, the biggest hack I can give you for graphing 1 over x. I don't know anyone who had me last year if you remember the trick. So I don't know who's present. Let me make sure. So Zareen or James or is Amelia here? I don't see Amelia. Do you guys remember the trick that I showed you for how to graph things that were like 1 over x or 12 over x, 6 over x, 8 over x? Do you guys remember that trick I gave you for that? Or if you didn't have me, maybe you know a trick that your teacher showed you for how to graph y equals a number over x.
Well, it just gets infinitely closer to the x-axis as it goes on, right? And then infinitely closer to the y as you get closer to...
Yeah, but there was something I gave you guys that like, if it were 12 over x, and you could get a lot of ordered pairs that were really precise for your graph. All right, ready? Don't worry, guys. I'll tell you. Ready? So if I rearrange this just a smidge in my head, which you guys are all going to be able to do, this is a fun way to do it. If I multiplied x on both sides, I'll get that x times y equals 1. So I use that to create points. Basically, I just need x and y when I multiply to be 1. So I could do 2 comma 1/2. I could do 1/2 comma 2, 3 comma 1/3, right? So anytime your x, y combo multiplies to give you 1, it'll be on that graph. That's another reason why, whether you look at it here or here, 0, no bueno, right? 0 cannot be involved because 0 times anything will not equal 1, or 0 in the denominator, no good because you cannot divide by 0. So I would not be able to do anything about this x in my denominator. It doesn't go away. This is a very strict restriction on your domain. X absolutely cannot equal 0. So remember when you found restrictions, it was what numbers can x not equal. This might have been something you did literally in September of last year. Like this was probably one of the first things you did in algebra 2. So x absolutely cannot equal 0, and it's a restriction. Your domain is like not allowed to have 0, the end. What do we call this purple dashed line? What's the name we learned in algebra for it? 2-word phrase. How about vertical asymptote? Spell asymptote correctly, please. You have a vertical asymptote in this example at x equals 0. Vertical lines are always x equals a number. I know the y-axis is vertical, but when y equals a number, it makes a horizontal line. Reason that out, eventually memorize it so you're faster, but if x equaled 5, 5, 0, 5, 1, 5, 2, 5, 3, 5, 4, it makes a vertical line, right? And if y equaled 5, 1 comma 5, 0 comma 5, 2 comma 5, it makes a horizontal line, all right? So where do vertical asymptotes come from? Like, where do babies come from? Okay, this is where do vertical asymptotes come from? They come from a very strict, can't do anything about it, restriction on your domain. But what else does this graph have? Zareen described it. She said it gets very, very close to the x-axis and very, very close to the y-axis, both of them. So not only does this graph have a vertical asymptote, but it also has what?
A horizontal asymptote.
Right. But where do horizontal asymptotes come from? If you could explain this to me, you will knock my socks off. I'll be so happy with you. Where do horizontal asymptotes come from? This is a major calculus concept. So if you are taking calc next year or in college or both, really want to wrap your mind around it. Don't take it for granted. So here, no one wants to guess? No risking for the biscuit?
Isn't it like, doesn't it have to do with Zeno's law? Because it's like you can keep infinitely going and making fractions and you'll never, like, they'll get smaller and smaller, but the bigger the number, the smaller the fraction will be.
I love that you remember I said that. Oh my gosh. A horizontal asymptote. So what Serene's referring to, mathematician, philosopher, ancient dude, Zenos with an X. He basically talked about if you get halfway closer, halfway closer, halfway closer, halfway closer, how you'll never actually get there, right? Because you can't ever take half of something and get zero. And once you are 0 miles away from something or 0 feet or inches away from something, then you're at that thing. So if you guys just get this 30-second ending, okay? So the horizontal asymptote, you might have learned in a different way, but one way we teach it in Algebra 2 is it's all about, link and left, all about end behavior. What's happening way at the end. Thanks a lot, guys. You can't wait 30 seconds. It's the last minute. I see everyone who's signing out. That's good. But it's, so I'm going to write the phrase end behavior. And what does that mean? The limit of the function, in this case, 1 over x, as x approaches infinity, and the limit as x approaches negative infinity of the function. So we are just introducing double limits in this to wrap up. If this was the function f of x, as x goes towards infinity, as x gets bigger and bigger and bigger, what does my function do? What does my y value of this graph get closer to in this example? Whether you do it visually from the graph or algebraically from the equation, just plug in bigger and bigger numbers from x. Any of you can tell me that. F of x gets, the function will get closer and closer to what number? As x gets bigger?
0.
Thank you. Come on, guys. Get that participation in. Same idea with negative infinity, 0. So a horizontal asymptote, that's why I reinforced the word strict before. Vertical is a strict restriction. You cannot cross it. But a horizontal asymptote, you can cross. It's only about the end behavior, and we'll talk more about that in the future. That all being said, this will be a transformation of this function over here to the left 2 units. It's this picture to the left 2 units, right? Did I write something down incorrectly? No. But I could just do direct sub right now. If I do direct sub, I will get 1 over 2 plus 2 and 1/4. But that graph would have been plus 2, 1, 2 to the left. You would have a graph like this. I'm just sketching it. We're going to talk more about rational functions in the next class. And over 2 up 1/4 will be a point on that graph. So the limit exists there. We'll start next class with an example. I'll write it down now so I just remember. For example, number, this will be 4. And we'll do the limit as x approaches -2 of x to the 3rd plus 8 over x plus 2. So we'll talk about that one. Otherwise, you guys are good to go. Actually, I'll write a 5th one for anyone who wants to copy it at this moment. Have a great weekend. Practice those formulas from the warm-up that we did. And the last one I'm going to throw over here. Let's do the limit as x approaches, I'm going to try to keep these sort of similar, x plus 3 over x squared plus 4x plus 3, and let's approach -1. So there we go. Those are the next two examples. They'll be in the next video. That was not necessary, that long fraction bar. Forgive me. Have a nice day.
Thank you.